Good morning. My name is Larry Cooper, and today I'm going to do a proof that explains that there are no solutions to the Diophantine equation x to the fourth plus y to the fourth is equal to z to the fourth. Okay? So here we go. It suffices to establish that x to the fourth plus y to the fourth is equal to z to the squared has no solutions. Neither can x to the fourth plus y to the fourth is equal to z to the fourth. So this implies this. Okay, so these are the lemmas that we're going to use today. There are infinitely many primitive Pythagorean triples, x, y, and z, with y being even. Then this is the form of each one. So you got x equals m squared minus n squared, y equals 2nm, z equals m squared plus n squared, where m, n are in z positive. You have lemma 2, the GCD of x, y is equal to 1. You have also, this implies that the GCD of y, z is equal to 1. And the GCD of xz is equal to 1. We also have lemma 3, where it says, let a and b in z positive. If the GCD of AB is equal to 1, then the GCD of A squared B squared is equal to 1. Then we also have the well-ordering principle. This is the big daddy of them all. This is the one that seals the deal. It states that every non-empty subset B of N has a least member bounded from below. So that's, again, each of these has a member bounded from below. So that means it's the minimum thing. It can't go lower than 0. Okay? So here we go. Here's the proof. Suppose that x to the fourth plus y to the fourth is equal to z squared has non-trivial solutions, x, y, and z positive, with the GCD of x, y is equal to 1. So we have that, since x to the fourth plus y to the fourth is equal to z squared, can be written as this, which is x squared squared plus y squared squared is equal to z squared by lemma 2, by lemma 2 from the solution to the Pythagorean triples. We know that there exists m and n such that x squared equals m squared minus n squared. There's a square right there. You got y squared is equal to 2mn. You have z is equal to m squared plus n squared. Now we can rewrite n squared plus x squared is equal to m squared. Since the GCD of mn is equal to 1, this is again a primitive Pythagorean triple, and since x is odd, n must be even. We have n equals 2rs, y equals r squared minus s squared. We have m equals r squared plus s squared, with the GCD of r and s equal to 1 by lemma 2. Substituting, we get m times n over 2 is equal to 2mn over 4, which you can rewrite as y to the fourth over 2, but you can also rewrite that as y squared over 2. Since m and n over 2 are relatively prime, they must be squares. Similarly, rs is equal to 2rs over 2 equals n over 2. As you can see, everything cancels out, is a square. So r and s must both be squares. So this is what we get now. We get, so r is equal to u squared, s is equal to v squared, and m is equal to w squared. So now you can take this and substitute back into the equation right up here, and you will see that you get w squared is equal to u to the fourth plus v to the fourth. Okay, so we end off with this. So now if we repeat this over and over, you're going to realize something. And I'm going to state it right here, but you guys figured it out yet? Well, here's the kicker. Since 0 less than w is a integer, and w to the fourth less than w to the fourth plus n squared is equal to m squared plus n squared is equal to z, we have that 0 is less than w is less than z. Now, what is this? This is basically relating to the term of infinite descent. It means you'll never exactly get to a final equation that will get you. You can always get a smaller z, and that's what we have stated here. So we have, and thus UVW gives a solution with a strictly smaller positive value. So you can make more substitutions, and you will see that you will get a smaller z value. You'll keep getting a smaller z value. So conclusion, by repeatedly applying the above, we obtain an infinite sequence of solutions of the equation x to the fourth plus y to the fourth is equal to z squared with smaller positive z values. This contradicts the well-ordering principle, which right over here, this is the well-ordering principle again. It states that every non-empty subset B of n naturals has at least member bounded from below. So this basically proves that there's no solution for this other than the non-trivial solution. Okay? And that concludes our proof. I'd just like to thank our author of the book for helping me with this. And credit goes to Kenneth Rosen, the elementary number theory. Thank you for your time.